So, hi, and welcome to my talk. Yeah, I've already been introduced, so maybe I don't need to repeat that. I'm going to briefly discuss sort of our AI research at H&M and a vision for a project we call HM2Vec, and I'll come to that in a minute. The agenda is basically this. We start with a little bit of philosophy, maybe sort of introducing how we think about the AI. Then I will introduce this project we have, HM2Vec, and after that go into a little bit more details on that project. The main relationship we have been working with in there and the implementation of that we have. And finally, of course, end with conclusion. But I wanted to start with this. Most of you probably know this guy. This is Hans Rosling, talking about the wonders of the washing machine. And I think this is a very interesting talk and a take that he has. A washing machine is something that was enabled with electricity, and as some of you have maybe heard, AI has been described as the new electricity. So I think sort of what is special about the washing machine? It is a rather simple engine or machine that was created with electricity, but it was incredibly valuable. And as Hans is quoted and quoting his mother, sort of having a washing machine means that now, Hans, we have loaded the laundry and the machine will make the work, and now we can go to the library. And in his talk, he's talking about a machine where you put in dirty laundry and out comes literacy. I think this is exactly what a company like H&M wants to do with AI, is creating machinery or algorithms or solutions that take a frequent and tedious task and automate it so people have physical and cognitive room for more valuable work. And that is what we are trying to do with what we call HM2Vec. First, I'll give a little bit of background. H&M is a fairly large company, I think we can safely say, which means we have hundreds of small tasks, small algorithms, or even big and use cases where we're trying to solve different problems. The problems can be demand forecasting, it can be a recommender system, it can be fashion forecasting, and all kinds of models. And as with most models, the more context we can give into the predictive part of the modeling, the more accurate it becomes. And most of the cases, the context we are working with clothing items. So the context means, for example, an image or a 3D sketch of an image when image is not available. It can be text description, it can be the composition, and many more items that describe the context. So how can we, if for all of these algorithms we have, which are in hundreds or even thousands, if all of them wanted to be state of the art, they would probably need a huge neural network with deep structures, processing images and text and all of this information, which is simply not practical in any engineering kind of way. So that is basically the idea behind what we call HM2Vec. And we are very much stealing or borrowing the name from Word2Vec. But if you think about words and natural language processing, I mean, words are nothing but random letters, basically. So how can you take words and sentences to sentimental analysis or automatic translation or predicting next word in search? What you need for that is a numerical representation of each word in a highly dimensional space, which has meaning, where you can calculate the distance between a man and a woman and king and queen, for example. And that's exactly what we are aiming for. We want to take away all of this load of processing the context, the image and text, etc., and pre-process that. So all of our use cases can basically just query a database or table, send in the item ID and get a feature vector back, which holds most of this information. We give away probably some accuracy for convenience. So that's the idea we have, but how can we get to this feature vector? So if you think about a clothing item, as mentioned before, there are multimodal description of an item. It can be the image, the text, the sketch, as I said before, and we basically group the rest in a tabular form. That could be the composition or the prototype or the season, etc. So if we can put all of this into some kind of embedding or feature vector, then we have solved this original part of so many of our problems. But embedding doesn't come out of itself. We need to train it or learn the embedding somehow. And the way we do that is through some kind of ground truth or relationship. The relationship can be very simple, just on the item itself. It can be some labeled attributes like color, type, or pattern. If we train an embedding on that kind of relationship, then we have a feature vector which can distinguish quite well between these attributes, different colors and different types, for example. But we also have other types of ground truths or relationships. For example, set of items or pairs of items, where we have fashion experts that have labeled our items saying these two items, they are compatible and other items are not. And that's a relationship where we can also train this kind of feature vector. And then that feature vector will be strong in telling us what is compatible and what is not. So basically a style flavored feature vector. And we could go further into sort of sequence of items, for example, the transaction history for customers. And then we would train a feature vector that sort of distinguishes between different purchase behaviors. We have looked into all of this, but we have come furthest with the compatibility part. So I'm going to dive a little bit deeper into that. What this means is that if we look on the left, we have a black sweater and a black skirt. And previously, this has often been the sort of solution that is available. You have this question, are these two items compatible or not? The same for the black sweater and the jeans. Are these items compatible or not? What we see is that you actually gain a lot of information by looking at other items that you know are compatible to the black sweater, for example, and to the black skirt. That can help a lot with predicting if the two items are actually compatible. And this introduces very naturally the concept of graphs. So we represent the compatibility as a knowledge graph, where edges mean items are compatible and no edges mean that they are not. So we can see that the querying such a knowledge graph can give different answers. If we are asking the network, do these leggings fit with which pair of shoes? It depends on the context, and now we can feed that into the solution. So it is context aware. And that brings us to our algorithm, which we call CA Cluster GCN, which is short for a very long name, Context Aware Cluster Graph Convolutional Network. This is the structure of it. We begin with feature vectors coming from RESTnet 50 trained on the ImageNet database. We decided to take sort of the frozen output of the network to begin with, but of course this could be trained end-to-end as well in the future. To control the sort of dimensions of what comes out of RESTnet, we added a shallow MLP on top of it, and then we have a trainable graph autoencoder. The graph autoencoder basically takes in the features of each item, which in this case was only the image, but could very easily be more of the models that we talked about. That's a part of our future work. We could feed in the text description and the tabular data in there as well. But we also feed in the adjacency matrix, which represents the knowledge graph of compatible items. And these two give us this embedding vector that we're talking about. And then we have the decoded part of this, basically predicting where we should have connections and where not. So in a masking kind of framework. This maybe explains it better. If we have the question, or is X1 or X2, are they compatible or not? We will encode the items there and their neighbors, and then have a decoder that can take these embeddings and answer the question. So if you look at the sort of family tree of this method, it is based a lot on the method called CA-GCN, which has shown very good results. We re-implemented it, experimented a little bit with the normalization of the adjacency matrix, and added a mini batch clustering part to it so that we could process bigger knowledge graphs. And most of this work is based on a master thesis we worked in collaboration with Danica and KTH, done by Georgios Telegeorgios. And if we look at the metrics we have, it is two kind of metrics. It is judging if an outfit is compatible or not. On the far left, we see an outfit that should be compatible, and the far right, we see an outfit that is not compatible. But we can also have a fill in the blank question, basically, where we have an incomplete outfit and we're predicting the missing item. And what we learned from this as well is that if we include the neighbors of the items in place, we are actually able to improve a lot the understanding of compatibility. Briefly about the data sets, sort of the baseline data set for compatibility has become this Maryland Polyword data set that was crowdsourced from users of this webpage called Polyword. We also test with an Amazon data set, which is looking at baskets and transaction history from users. And we have the parallel industrial data sets where we have the pairwise compatible data for outfits and transactional data as well. And if you look at the results, we include here some historical results as well, but the main focus here is sort of on the previous method. And for Maryland Polyword, which is a rather small data set, there isn't really that much difference between the methods, but we show that we're able to improve the previous method a little bit with the different kind of normalization of the adjacency matrix. What we think is very interesting here is that if we don't include the neighbors in the encoding, we are actually doing pretty badly. So we are really learning about the style from the neighbors, which is an important learning, we think. We also sort of tried this on our internal data set and be aware, I mean, this is not apple to apple, it's a different kind of data sets. For example, the number of items in each outfit in the Maryland Polyword data set is twice as much as in the H&M data set. But we see that we are able to learn fairly well, but this is ongoing work and we hope we can improve it even more. If you look at the transaction part of it, the transaction history for customers, or it can be the transaction history, which is sort of also bought, and bought together is basically the basket, the things you buy at the same time. And again, here, if you look at CA-GCN and the CA Cluster GCN, we see that we are able to improve it a little bit, and we see that as the knowledge graph increases, the sort of mini batch method is starting to help out with the training. And note that I don't have time to go into the mini batch part, but having mini batch or batch approach for a graph is absolutely non-trivial. I mean, if you start to break up the graph, you start to lose information. But you can read, if you want more details, I will sort of ask you to maybe read the master thesis. It's pretty well written. Again, the neighbors are very important. And if you look at our internal data sets, again, not apples to apples, but we are able to get some meaningful information, more for women where we have more data. And an interesting last point, just a curiosity basically, but it could lead to something on its own. is that we tried transfer learning, where we only look at the decoded part and continue training the decoded part, trying to understand the personal transaction history. So basically creating a recommender system or an understanding of how to predict purchases personally on that. I mean, the results are not awesome for this, but this was just a curiosity we did in the end, but could lead to something more. So if we conclude on this, what we have is a graph-based model which works very well for item-to-item relationship with sparse connections. I mean, when we have more and denser connections, this is probably not the best solution. But when the connections and relationship are rather sparse and have a lot of meaning, this seems to be a very good approach. We can use this to complete an outfit, evaluate compatibility of an outfit. If we had other ground truths, for example, like similarity between items, the same method could work very well. And in the HM2Vec framework, that would then give us a different flavor, a flavor for similarity instead of style. It doesn't have to be exactly the same thing. And we thought it was very interesting to try out the transfer learning, which can lead to more future work. The model can, and it is chosen and built in that way that it can easily work with multimodal input like image, text, sketches, etc. And actually the sketch and image part is very interesting because using 3D sketches instead of the image can be very important. It's not, the 3D sketches are not photorealistic, they're fairly good, but in many of our use cases, we are taking decisions before we have been able to take a picture of the product. I mean, maybe we haven't even produced the product. So it is very important to be able to be robust and flexible towards the input. Well, probably the most important part here is this sort of, where I started with Hans Rosling, this kind of washing machine AI. So we are able to provide style-focused HM2Vec representation. And we can easily have different flavors there. If we train on a different kind of relationship, we can have a different kind of feature vector that use cases can pick up depending on what kind of project they're working on. There is ongoing work with other types of relationship. We have some work on transformer models for sequence of data, that's meaning transaction history. And of course, some analysis on the sort of color and type part of it, the most basic relationship. And the immediate future work that we have already started to plan is to continue with a graph network which can use knowledge graphs based on the compatibility, as we talked about, as well as the transactions, and combine them. We think we can do a much smarter way in combining or including the transactions into this knowledge graph. We did it in the most simplest way. If we can add some association mining on top of it so that the edges have more meaning, we think we can gain a lot with that. That's basically my talk. I mean, if this is recorded, it's good to have the references and also refer you to the thesis. Otherwise, thank you.
Thank you so much, Stefan, and thank you for reminding me that the talks will be recorded, so that for those that will want more information or actually have enough time to read the list of references, they will be able to do that afterwards. This was excellent, and I have to say there are so many interesting questions in the Q&A section, which I will really ask you, Stefan, if you have time, please do address them, because they are both technical nature, but they also have to do with kind of like more, how can I say, the idea of basically using AI to understand kind of like human perception of fashion, but also generate new trends. So the effect on a human, how do we kind of like change the perception of style, for example, by you know, having AI system generating suggestions for us. So the question maybe interesting is what Alessandro has asked. So it's about the recommendation systems, I think, a little bit in general. So a good fashion designer finds new trends rather than following trends. Do you think that that will also be an idea? And is that a challenge? Is there a challenge of actually using AI tools in the construction process where designers, need to now use tools rather than do business as usual?
Yes, I mean, this is a repeated pattern. I often think about my Spotify list of music. I mean, you start listening to something and then they suggest what you listen to. So you're always bootstrapping yourself and others at the same time. So it is really this kind of combination. You really need innovation, otherwise everybody gets stuck in the same group. Mm. But after that, you really do this bootstrapping and you sort of fine tune towards something. And that is what most of these algorithms really do. Mm. I mean, you try to squeeze out the signal from something noisy and you end up in a group that is somewhat similar to you.
Right. No, so I think that's interesting. So the point is now very much is targeted towards customers, but I think it's also going to be a tool for the designers.
Yes.
To work more and use it more in the future. And also regarding one of the Amy's comments, which was towards sustainability, making sustainable choices based on recommendations that come from AI systems. Mm-hmm. Stefan, thank you so much once again. If you have time, please do answer questions in the Q&A by typing. Yeah, thank you so much.
And thank you for inviting me.